Welcome to a new video. In this video, we're going to be talking about direction fields, which are a geometric interpretation of first-order differential equations. So we need to remind ourselves, what does the derivative represent geometrically? And if you think back to Calculus 1, you'll remind yourself that the derivative represents the slope of the tangent line. So what we're going to do is we're going to take this example, this first order differential equation, dy over dx equals x minus 1, and we want to find the slope of the tangent line to the solution function at the point 1, 1. We want to figure out what is the slope of the tangent line at 1, 1. Well, how do we do that? And the answer is we'll just take the value for x, which is 1, and we'll take the value for y, which is also 1, and plug them into the differential equation. And that is the slope. So we have a slope of 0 at the point 1, 1. So what does this look like geometrically? Well, let's graph the xy plane, and we're going to highlight this point 1, 1, which is the larger dot, and we know that it has a slope of 0 at this point. And if you recall, a line with slope 0 is just a horizontal line. So we're just going to draw a very faint and small horizontal tick mark at the point 1, 1, and then we're going to just create a little table over here on the right-hand side. Because there was nothing special about 1, 1. We can plug in any point we want and figure out what the slope of that associated tangent line happens to be. So let's take the point 2, 2, which when we plug that in, again, 2 minus 2 gives us 0. So at the point 2, 2, we also have a slope of the tangent line equaling 0. And you might recognize that for every single point where the x and y coordinates are equal, the slope of the tangent line is 0. So for every point along here where y is equal to x, we have a horizontal tangent line at that point. So we're going to draw a faint horizontal tick mark. So let's take a couple of other points. So let's take the point -2, 2. When I plug that in to the differential equation, -2 minus 2 is equal to -4. So at the point -2, 2, in that second quadrant, we're going to draw a little tick mark whose slope is -4. We could also do the same thing for 1, -1, and I'm just picking random points here. And I'm calculating x minus y for that point to give us the slope. And at this point, 1, -1, the slope happens to be 2. And we can do this for every single point in this grid. And we get a graph that looks like the following. This graph here is called a direction field. And this direction field is associated with this differential equation. So I'm just going to blow up the direction field a little bit so it's a little bit bigger. And here's what it's going to end up looking like. And now, let's say that we were also given some initial condition. Let's say we know that the solution to this differential equation also has to go through the point 0, 1, which I've drawn in red here. Well, remember what this tangent line here means, or the slope of the tangent line. It means that the graph is sort of going in a downward trajectory here. And the idea is to sort of follow the lines of this direction field to get a geometric interpretation of what that solution happens to be. And at least if we follow along the direction field here, it looks like this is what the solution would look like to this first order initial value problem. So let's look at another example. Let's take this direction field. dy over dx is equal to y times 1 minus y. We're going to sketch the direction field for it, and then we're also going to sketch the solution through the point 1, 2. Well, I've written the IVP at the very top, and we're just going to start picking some random points. So I'm just going to pick the origin. And notice, if I pick 0 for x and 0 for y, when I plug those in, y times y minus 1 gives us 0. So at the origin, the slope of the tangent line is 0. And in fact, you might recognize no matter what the x-coordinate is, if the y-coordinate is 0, because of this condition right here, or this term right here, the whole slope will end up being 0. So every single point along the x-axis, no matter what the x value is, if the y value is equal to 0, then the slope of the tangent line is equal to 0. So we have horizontal tick marks along the x-axis. And notice, no matter what x is, if I choose the y value 1, then 1 minus 1 will equal 0, giving us horizontal tangent lines for every single point where the y-coordinate is equal to 1. And in fact, you might be recognizing that because this derivative is independent of the x variable, that we only care about what y is. So we just need to pick a bunch of values for y and figure out what the slope is for all of those particular points. So for instance, if I take the y value equal to 1/2, so right in between, then all of those slopes of the tangent line will be -1/4. If I move up to 2 with the y value equal to 2, then every single slope is 2 times 2 minus 1, or just 2. And then we can fill in the rest of the table the same way. So notice in this grid here, there are 64 different dots, but I didn't have to find the slopes at every single one of them. The idea was I looked for some patterns and recognized that the x-coordinate didn't matter, and all I had to do was calculate one slope at, the slope at one particular point, and then duplicate it left and right because of that independence of the x variable. So now remember, we're also trying to sketch the solution through the point 1, 2, which is this point in red here. And if you want to pause the video, go ahead and see if you can figure out what that sketch looks like. And it should look something like this. It should look sort of like the exponential function, e to the x. Okay, it's not exactly the same thing as e to the x, but it has the overall shape associated to it. But what happens if I would have chosen a different initial condition? So what if it was going, the solution went through the point, let's say 1, 1/2. Well, the solution is going to look different. It's probably going to look more like this, because it has to fall in between 0 and 1, because these are sort of acting like asymptotes. And then furthermore, what if I would have picked something in the fourth quadrant, like this point? What would the solution look like? And if you said it looks something like this, then you would be correct as well. So the initial condition will give you what the overall shape of the solution looks like, but the direction field is just a general graph of what all of the solutions, or the family of the solutions, happens to look like. Now, I want to say one last thing before we finish this video, which is when you're drawing direction fields, you want to look for patterns. So for example, this last example we did is what's called an autonomous differential equation. And an autonomous differential equation is one where the derivative only depends on the y variable. So what we did was we recognized that it didn't matter what x was. We just picked some random values for y, and then everything along that horizontal line had the same slope. So no matter what x was, x, 0 will give a slope of 0, x, 1 will give a slope of 0, etc. So if you look back at our direction field, then all of these points here have slope 2. All of these points have slope 12. All of these points also have slope 2. So we could just sort of find what the slope is at each of the points along the y-axis, and then due to the autonomous nature of the differential equation, duplicate those slopes left and right. Okay, so that's what you can do with autonomous differential equations. But if we go back to our first example, this is not an autonomous differential equation. However, if we just choose a random value for m and set, remember this derivative is the slope, if we set this x minus y equal to m, then every single point that satisfies this equation will have the same slope. And if I solve this equation for y, I get y equals x minus m. So every single point that satisfies y equals x minus m will have a slope of m. And this will greatly simplify our lives, so we don't have to plug in every single point. We could just pick a couple values for m and look for the pattern. So if you recall, this was our first direction field that we created. And notice if I choose m equals 0, that gives me the line y equals x, and every single point along y equals x has a slope of 0. If I chose m equals 1, then that's the point y equals x minus 1, which is this line, and every single point along this line has a slope of 1. I can go all the way up here and choose m equals -2, which gives us the line y equals x plus 2, which are these points. And in this case, you will find that every single point along this line has a slope of -2. So this can greatly simplify your direction field calculations, because you don't have to find every single point individually. You can sort of look for patterns and spot when multiple points will have the same slope. Okay, so the idea is take this function f of x, y, set it equal to m. Every single point that satisfies this particular equation will have a slope of m. And that might save you a little bit of time when you are drawing your direction fields. So, I hope this introductory helps somebody. Good luck on direction fields.